Okay, so today we're going to talk about prime and composite numbers. Let's start with a sort of a thought experiment here. Let's take a look at the number 12, for example. Um, let's imagine that I give you a bunch of blocks, and I want you to make a rectangular shape comprised of these blocks. What are the dimensions of the rectangle that we could create? Okay, so one could be a 1 by 12 block. What other shapes could we come up with? Somebody else could do a 3 by 4. Someone else could do a 2 by 6. And then I'd ask, is there any other ways that we could set up the area of these rectangles or any other configuration? And someone would go, well, we got 4 out of 3. And you go, well, 3 and 4 and a 4 and a 3 are the same shape. Okay. What about the number 7? Obviously, we could do a 1 by 7. But that's pretty much it at that point. We don't really have any other way to rearrange the individual pieces to generate a rectangle of some kind. So there's got to be something different about the numbers 12 and the number 7. And the definition that we come up with is that 7 we define as a prime number, and 12 we define as a composite number. Okay. But let's kind of continue with this idea of developing number of factors that a number has. Okay, so let's go back to that sort of area activity, and let's think about just a list of numbers here. So let me start with the 1. Try that again. Okay, so with the number 1, what multiplies to give us 1? Just 1. That's it. 1 times itself. The number 2, we get 1 times 2. The number 3, we get 1 times 3. 4 is a little more interesting. We get 1 times 4, and then 2 times 2. 5, we get 1 times 5. So if we make this list, let me get 6 real quick. 1 and 6, 2 times 3. Right, if we make this list, and we could go out as far as we wanted to go, but we generate sort of this list of numbers and who's got so many factors. Okay, so let me kind of make a sort of a makeshift chart here, and we're going to label this the number of positive divisors. Okay, and under the column 1, what number has only one divisor? That'd just be the number 1. 2 divisors, well, so far on our list we have 2, 3, and 5. Under 3 divisors, we've got 4 so far. Number 4, sorry. 4 divisors, we have the number 6. And I'm just going to go out to, sorry, that was supposed to be a 5. And we'll just go out to 6. Okay. And so if I keep going through this activity of thinking of how many different things there are, 7 would just be 1 and 7, so that would be on the 2 list. 8 would be 1 and 8, 2 and 4, and so it would be under the 4 list. 9 would be 1 and 9, and then 3 times 3, so it would be in that list, the 3 list. And so we can sort of keep going. 10, let's see, 10 would have 4 divisors. 11 would just have 2. Let's see, 12. 12 would be over in 6. Yeah, let me look at 12 with you real quick. 12 would be 1 and 12, 2 and 6, 3 and 4. So we have 1, 2, 3, 4, 5, 6 divisors. Okay. Now, in looking at this chart where we've broken up numbers, this column right here is where we find our prime numbers, and the rest of this column are where we find our composite numbers. Okay, so sort of another visual way that we can see what makes something prime versus what makes something composite. Okay, so that brings up a series of definitions. The first one, any positive integer with two distinct positive divisors, just two, we define that to be a prime number. Any integer greater than 1 that has a positive factor other than 1 in itself, in other words, it doesn't fit in the prime category, we call that a composite number. Then we have each expression of a number as a product of factors. So when we take a number and we rewrite it in terms of the things that make it up, we refer to that process as the factorization. Factorization containing only prime numbers is called a prime factorization. Okay, and then this lovely statement, each composite number can be written as a product of primes in one and only one way, except for the order of the prime factors in the product. This is called, oddly enough, the fundamental theorem of arithmetic. Or the unique factorization theorem. And the short sense is we can take any number and there's only one way to write it up as a set of factors, prime factors. The only thing that might differ between kids in the room is, I put a 2 first, I put a 3 first. You just tell them to put it in numerical order, then they can see, that they've all got the same prime factorization. There's only one prime factorization for any given number out there. Okay, so I want to do a couple of quick illustrations about this whole prime factorization theorem and some just general techniques and how we can get students to understand this. One way to do it is a nice good old-fashioned factor tree. So just take 24, for example, and what do we know for sure goes into it? I know 2 times 12. Okay, 2 is a prime number, so I'm going to stop with that part of the tree, and I'm going to go back to 12. I know 2 times 6, so I'll stop there. I know 2 times 3, and those are all prime. Okay, I'm going to do this a different way, because I hear students all the time go, mine's different. Clearly I'm wrong, or you're wrong. And sometimes in math, different does not mean wrong. What if we went 3 times 8? That also gives me 24. And 8 would be 4 times 2, and 4 is 2 and 2. Notice what we have, right? So when you get down to the bottom, how many 2's are there? There's 2 to the 3rd power times 3, and that's the same for both charts. So different does not necessarily mean wrong, just means different. And if they go down to prime factorization, they can see that they got the same set of numbers. Okay. Let me do a bigger number, something that we might not necessarily see. 7,875. Well, looking at it, I know I can break that up into 5 times something. So I'm going to divide that by 5. Now off screen you don't see this, but I actually do have a calculator that I'm staring at. So I think that's a kind of a big number. Let's see. 15,075. I know 5 goes in there again. So 315. And again, divisibility rules, I can see that 5 is going to go in there one more time. Okay, so then what goes into 63? Well, I know 9 does, and 7. And 9 is 3 times 3. So let me collect up all of my prime numbers. So 7,875 can be written as 3 squared times 5 cubed times 7. There's only one way to write that number, and that's in that way with those prime factors.